Okay, so let's start. A reminder. So I think that registration is solved. All the people that wanted to be in the class are in the class. I may have not signed all the forms. If you have a form that needs signed, come after class. But I think it's done. The key thing is that I want to remind you that we have 2 lectures today. One is now, and another one at 5 here. Questions? Issues? Anything? Okay. So another thing I want to remind you is that many of you, about 70 or something like this, are registered for 4 units. So you have to think about projects, team up, and ask questions. I'm going to actually give one example later today of something that could be an interesting project, but you know, there's infinitely many possibilities for interesting projects. Questions on this? Okay, so let's remind you where we are. So last time we started talking about linear learning algorithms and try with the attempt to quantify them. Specifically, we started talking about Perceptron that we're going to talk a lot more about today. And the game we're playing is very simple. We're going to think about it as an online learning algorithm where we try to learn a function that maps x to plus or minus 1. X could be either Boolean vectors or real-valued vectors. We're going to learn a weight vector that is a real-valued weight vector, and we're going to be given a sequence of examples, x1, y1, x2, y2, and so on. Before we get to details, I want to just kind of place it in the position it of where we left off, or what are the issues that we discussed last time. So one issue is we're talking about mistake-driven algorithm. So currently, the algorithm is not going to make a change in their hypothesis every time they see an example, but rather only when they make a mistake. So You take an example, you make a prediction using your current hypothesis. If it's okay, you don't change it. You believe that your hypothesis is right, and so on. And this is a very simple, very natural protocol, and will also allow us, as you'll see, to actually show some powerful results. So the analysis that we're going to provide is going to be via this mistake bound, right? So we look at mistake-driven algorithms, so we care about how many mistakes the algorithm makes until it's done, maybe stop making mistakes, or at least doesn't make a lot of mistakes. And we actually proved that for the finite hypothesis class case, an algorithm, a generic algorithm, can be bounded in terms of number of mistakes. Right? So you remember, hopefully, that we discussed this. And it's a natural question, is this a general thing? I mean, can we say the same thing about cases where the hypothesis space is infinite, right? So when we talk about general linear classifiers, where the decision is a dot product between a real value W and X, the size of the hypothesis class is infinite. Can we bound the mistakes? And this is actually one of the key things we want to talk about today. Okay, so here's the algorithm. Very simple algorithm. We initialize the weight vector to 0. For example, cycle through all examples, predict the label of an instance X to be Y prime is the sign of the dot product. If we made a mistake, that is, if the prediction is different than the label, then we update the weight vector, and we update it in an additive way. So we take the old W, and we add Y times X times some number that we're going to call a learning rate, which means if Y is positive, which means the example is positive, we thought it's negative, we're going to add X to W. If Y is negative, it's a negative example, we thought it's positive, we're going to subtract X from W. That is. So this is an illustration that we went through last time, so I can just run through this. This is the line, the decision line. So this is the line Wx equals 0. Red points are going to be positive, so I want that for the red points, Wx is going to be positive. For the blue points that are negative, I want Wx to be negative. And if it's not the case, then we're going to modify it. So for example, this is my current W perpendicular to this decision surface Wx equals 0. I made a mistake on a red point, and therefore it's a positive point, so I'm adding the example. This is the example. I'm placing it here. I'm adding it to X, and I'm getting this as my new hypothesis, and so on. So now we can continue with this. Another positive example that we made a mistake on because it's on the wrong side of the hyperplane here. And again, I'm going to add it to my current hypothesis, and I'm going to get this hypothesis. This is already enough. Okay, so that's the algorithm. Questions on the algorithm? Okay, so we ended up last time by saying that there are two types of things you may want to say about an algorithm, and these are actually statements that are kind of a little bit hand-wavy that were given in the 50s by Rosenblatt when he invented Perceptron. One of them was about convergence. He basically said if the data is linearly separable, right? This is a data-dependent statement. If the data is linearly separable, which means there exists a hyperplane that separates positive from negative, then Perceptron will converge to it. He didn't say how long it's going to take, but he knew it's going to converge to it. And he also said that if it's not linearly separable, it's not going to converge to it, and it's going to cycle through this. So we're going to try to address these two statements in a more quantitative way, in a more modern way, if you want, but it's not going to be that modern because this was known a long time ago. Just another way of writing the algorithm in order to make sure that when you see it somewhere else, you'll make sure it's the same algorithm. So remember that we suggested the generic conversion from the n-dimensional space to the n+1 dimensional space, avoiding using the theta. But I want to make sure that you know that actually, by doing this conversion to the n plus 1 dimensional space, I essentially place the theta as the n plus 1 dimension of W. So I'm updating theta whenever I update W, right? So here I'm just writing this explicitly. So for every example, I'm predicting as the sign of Wx minus theta. If I made a mistake, I'm updating both W and theta. Just another way of writing it. It's exactly the same algorithm. In fact, I'm going to use most of the time the n plus 1 dimension representation without calling it n plus 1, just assuming that the hyperplane goes to the origin. OK. So now that we understand that we learn both W and theta, we can actually say something about it. So what I'm going to prove is I'm going to prove that perceptron has a mistake bound. And this is an old theorem from the 60s, still very powerful and important. So again, the algorithm maintains a weight vector W. When we receive an example X, we predict according to the current linear threshold function, Wx greater than 0. We say yes, otherwise we say no. So what does the theorem, Novikov's theorem, says? This is our data, let x1, y1 up to xt, yt be a sequence of labeled examples where the xi's are real-valued vectors. And the size of xi is bounded by R. Is this a strong assumption? Yes, no? Only two options? Not an assumption at all, right? Because I gave you a finite set of x's. Clearly, there is some R that bounds the size of all these x's, right? Takes the max over all the examples, right? So it's just a notation, right? I can always say this. Yi is plus or minus 1. Now, here is an assumption. I'm assuming that there is some u, some vector u, that actually separates the data. So I'm assuming that the data is linearly separable. Moreover, I'm assuming that there is some gamma here, a positive number, such that, and I'm also assuming that the size of u is 1. So again, I'm assuming that u separates the data, and that its size, the size of the separator, is 1. Is this a big assumption? Yes, no? No, why not? Right, so if you give me a u that separates the data, I can always, and the size of u is 17, I can always multiply everything by 1 over 17 and get a u that does exactly the same thing, and its size is 1. So I can always, it's just a technical assumption that is going to be convenient. Right? I can always do this by scaling. But I'm assuming here that yi, the label, times u dot product with xi is greater or equal to gamma for all I. So first of all, let's read this. This is one statement that actually can be read in two ways. If y is positive, it's a positive example, then I'm saying that the dot product u dot xi is greater than gamma. If it's negative, it's minus 1, I'm actually saying that the dot product is less than minus gamma, right? So essentially, I'm taking some width around my linear separator and saying that the data is outside it. Now, is this a big assumption? I told you that the data is linearly separable. I'm assuming that. Is having this gamma a big assumption? Yes, no? Yeah? Right, so it's not an assumption. It's actually there in the data. If I'm assuming that it's linearly separable, and I have a finite set of examples, t examples here, I can go to the closest example to the line and choose its distance from the line to be this gamma. And now all the examples are going to satisfy. For all I, I'm going to get this. Right? So whenever I have this finite sample that is linearly separate, I have this gamma. Okay? Now, you could imagine that this gamma actually represents how difficult the data is. If it's really tiny, it means that there are examples that are very close to the linear separators. My problem is going to be harder, because it's going to be hard to fit this linear separator there. If gamma is large, it's going to be easy to fit something between the positive and negative examples. So it's natural to think about this gamma as a complexity parameter of my problem, but it's there always. Okay? Okay, so these are the conditions. Under these conditions, the claim is that Perceptron is going to make at most R square over gamma square mistakes on this example sequence. Now, again, try to understand what that means. This R square is just the size of the data. If the examples are farther apart, it's going to influence how many mistakes I'm going to make. But the most important thing is this, and it's very natural. So if gamma is small, you're going to make more mistakes, because it means that you have points that are close to the separator. And it's going to take time for you to fit it such that you will not make mistakes. If gamma is large, then you're going to make less mistakes. So it's natural to assume that this is inversely proportional to gamma. Yeah?
So the equation should left side have a...
No, because I don't need it. So this could be either +1 or -1. So if it's +1, basically what I'm saying here, that this is greater than gamma. If it's -1, essentially this says that the dot product is less than minus gamma. Right? So you can write it twice. Once for positive example, once for negative example. But I just wrote it in one statement for all examples. Okay? It's essentially something that you've seen in the problems, in the first problem set. We've written it both ways. But here I'm just collapsing it to one inequality. Okay, so let's try to prove it. And in fact, it turns out that it's not difficult to prove what we want to do. So I'm going to use the following notation. So VK, V is going to be my weight vector. VK is going to be the hypothesis, the weight vector before the kth mistake. Remember that what I do here is I count mistakes. I'm assuming that the kth mistake happened on this example, on the ith example, and therefore, I know this. I know that yi times vk dot product with xi is negative or not positive. Why is that? Just a definition of a mistake, right? Now, notice that the reason I'm writing it this way, this is another component of the answer to you, is that here I don't need to care about whether I made a mistake on positive or a negative example, right? I just say that the sign of yi is different than the sign of the dot product. That means a mistake. Either it's positive and the dot product was negative or vice versa. Okay? So now, these are the assumptions that we were making. We should keep it here because it's going to help us in the proof. We start with V1 being the 0 vector. We are assuming that U, the separator, is 1, norm 1. And we are assuming that for all I, the data is linearly separable, and this is satisfied. Okay, so now I'm going to compute VK plus 1. I'm just updating because I made a mistake. So VK plus 1 is going to be VK plus YI XI, right? My R, my learning rate, is 1 here, so I don't even write it. That's just the Perceptron update rule. Now I'm going to compute the dot product between VK plus 1 and U, because it's going to help me prove something. So the dot product between VK plus 1 and U is just I'm taking this and multiplying by U, VKU plus YI dot product of U and XI. I'm claiming that this is greater than VK times U. I'm just copying this here, plus gamma. Why is that? of this. Just because I made a mistake, right, on x, y, yi, and therefore gamma is greater than this guy. Okay? Okay, so I got this for one step. I have vk plus 1 times u greater than vk times u plus something. I can recurse this k times. Every time I'm gaining a gamma here. So if I do this k times, I'm going to get that vk plus 1 dot product u is greater than k times gamma. Okay? And I'm going to remember this. So this is one result that we care about. The second direction, I'm going to reason about the norm of the weight vector, the norm of vk plus 1. So let's just compute this. The norm square of vk plus 1, vk plus 1 by definition of the perceptron rule is this. So let's just square this. So I'm getting vk square plus 2 times vk dot product with xi times yi, it's this, plus twice xi, because yi is plus or minus 1, so it disappears here when I square it. Okay? So this is just squaring the update rule. And now I'm claiming that this is less than equal than vk square, I just copy this, plus r square. So I did two things. First of all, this disappeared. Why did it disappear? Why is it okay? This is negative, right? Because I made a mistake. It's written here. This guy is negative, so omitting it just grows this. And this guy, by our assumption, is greater than r squared, so I can replace it by r squared. Okay? So now again, I got the following inequality. vk plus 1 squared less than vk squared plus something. And again, I can recurse it. I can repeat it k times. Every time I'm reducing the index, and I'm adding r squared. But v1 is 0, so I'm going to get the vk plus 1 square is less than k times r squared. Okay? So actually, very simple thing. All I did is just use the update rule and my assumption. So now I can put these two together, the two inequalities with the 3 dots here. So what I have is this. vk plus 1, I'm taking the square root. On one hand, it's less than square root of kr from here. I claim that always vk plus 1 norm is greater than vk plus 1 dot product u. And because of the first part, vk plus 1 dot product u is greater than k gamma. So the only thing you really have to think about here is why did I claim that this is greater than? Why is that? So it's due to the assumption that u, the size of u is less than 1. You actually have to do a little bit of trivial algebra here. You have to know the definition of dot product. Right? But you can write for yourself what is the dot product. Write it for yourself from the definition, and then you'll use the fact that u is less than 1 and cosine is less than 1, and you will get this. Okay, so basically, we got this relation between square root k of r times r and k lambda, and from these two, I can just get that k must be less than r squared over gamma squared. So the number of mistakes I'm going to make is going to be bounded by this, which is, in some sense, if you think, is kind of magical, right? Because I'm living in an infinite space. Nevertheless, after a small number, or at least a finite number, that depends on the natural complexity parameter of the problems, I'm going to be done. We'll never make more mistakes. And this is irrespective of how you present the data to me, right? Which is very nice. Okay. And this is a really important problem. It's important to note that the bound doesn't depend on dimensionality, at least not directly. A little bit it depends on it because the size of the data, r squared, is a function of dimensionality, but not directly. it doesn't depend on the number of examples, right? So we are living in a mistake-driven protocol. I don't care how many examples you give me. I only care about how many mistakes I'm making, because this is where the work is. So this is important. And another thing that will be, it's trivial, but will be important to understand, because there is something deep about it, is that for us, weight vectors, v's in this case, and examples, x in this case, they live in the same place, right? In the same space, right? We add them, we compute dot products, everything is the same space for us, even though semantically they're different things, right? This is example, this is the hypothesis space. And that's going to be important when later on we move to other representation of the same hypothesis class. We're going to call it dual representations. But for now, it's important for you to kind of realize that the weight vector is in fact a sum of examples, right? You start with 0, and then you add examples. And that's how you grow or develop your weight vector. Okay, so now we want to, so this was very nice, I think, but only for the case of linearly separable data sets. And you could argue, in many cases, the data isn't linearly separable. Is this going to break down? So here is a simple generalization of the perceptron rule. And before we want to generalize, we want to think about how to generalize. So we care about the non-separable data, and we want to think about how to quantify the fact that it's non-separable, right? So basically, I need to measure what does it mean for me to fail to have a margin gamma, right? So this is the data that I have. This is the margin gamma. If everything was linearly separable, then all the red points will be outside this dotted line, and all the purple points will be outside the dotted line. And what happens here is that they're not. So some of them are within this gap, and some of them might even go to the other side, like this positive point that went to the other side, right? So that's what it means to be non-separable. How do I quantify? So I want to quantify it using this slack variable, chi, or psi, and I'm going to measure it this way. I'm going to look at the maximum between 0 and the difference between gamma and yi times the dot product. So let's just think about what this means, right? So we actually looked at it before. So before, when it was linearly separable, we said that this guy is always greater than gamma, right? It's outside kind of this width of the linear separator. So this is going to be negative when everything is good, right? Everyone agrees? This part is going to be negative when everything is good, and therefore psi is going to be 0, the maximum between 0 and something negative. So when everything is good, this is going to be 0. When it's not 0, it means that we're not separable, and we're going to, and psi is going to quantify it, and it's going to grow linearly with this dot product. The larger the dot product is, the larger the slack is. Okay? So this is a way, not the only way, but a good way, it turns out, to quantify how non-linearly separable we are. And this function by itself, we're going to see it later today again, or maybe, yeah, definitely later today, maybe in the afternoon, is actually a very important function. So as a function of this psi, now I can quantify the behavior of the algorithm. So first of all, I'm going to denote D2 is going to be the L2, the sum of all psi I square over all the data that I have, right? So every example has its own psi I that measures how far it is from obeying the separability constraint. And the theorem says that the perceptron is guaranteed to make no more than R plus D over gamma square mistakes on any sequence of examples satisfying that all the examples are within an R ball. So what have we done? Actually, it's almost the same bound that we had before. It's R over gamma all square. Now we just added these psi square. So basically, we said, well, it's non-linearly separable, which means we're going to make more mistakes, but we can quantify how many more mistakes as a function of how non-linearly separable we are. Okay? Questions? Okay, excellent question. So basically what you're saying is that this bound really depends on gamma. Because if I choose, if I replace gamma, D2 is going to change also. So really, to make this a bound, you need to optimize this over all values of gamma, which I'm not going to do here. Here I care just about quantifying this in a theorem. In practice, if you want to know, given a data set, what's going to be the bound, it's an optimization problem over gamma, right? So you have to play with gamma as a function of it. Given the data, D2 is going to change, and this is going to change your bound. If you want to find the best one, we have to optimize this function. I'm not going to prove it. It's actually not much more difficult than the previous proof. And on the website, for people that are interested, we're going to point to a paper that, that proves this. OK. From our perspective now, it's important to realize that perceptron is actually robust to noise. This was one worry that, in fact, early on, when people introduced perceptron and started playing with it, wasn't clear. This is a relatively recent result, recent as in about 10 years ago. OK, so I want to move now to another algorithm or another family of algorithms. And in order to really think about it in an easy comparative way, I'm going to go back to talking about Boolean functions. So we proved something nice about perceptron. But it turns out that if you think about Boolean functions, it's not as nice as it could have been. For example, if you go back to this K disjunction or K conjunctions problem that we talked about last time, that is, the target function is a conjunction, is a disjunction, in fact, in this case. But only K of the variables are actually active. We don't know which K, but we know that out of the N possible variables, only K are actually important. It turns out that one can find a sequence of examples that will cause perceptron to make O of N mistakes. Even though, so N is the dimensionality, only K are important, nevertheless it will make order of N mistakes. And last time we kind of, we said that we may not want this to happen. We may want to be able to think about algorithms that depend on N, but depend only weakly on N and mostly on this K. So now I want to introduce an algorithm that actually can satisfy this. Last time we gave a very generic in-principle algorithm. It wasn't really something that you can compute because it required you to access quickly all the hypothesis space. Now I'm going to give a realistic algorithm that actually has this behavior. And the algorithm is called Winnow. I'm going to present now just a very simple version of Winnow. It's as general as a perceptron. I'm going to present it now just so that we'll understand in the case of disjunction and conjunction, kind of Boolean function, because this, it's easy to show a proof in this case. The general proof is much harder than the perceptron proof. So let's just look at the algorithm. Again, it's a dot product algorithm. I'm going to make decisions in this case based on whether Wx is greater than theta. Notice that here I left the theta outside. I'm going back to my n-dimensional representation. And I'm going to assume that I'm initializing with W equal 1, Wi is equal 1, and theta is going to be n, my dimensionality. Again, it's a mistake-driven algorithm. If I make no mistakes, I don't update the hypothesis. If I do make a mistake, on positive examples, I made a mistake, which means the dot product is less than theta. I'm going to replace Wi by 2Wi. Rather than adding something, now I'm multiplying by something. If I made a mistake on a negative example, I'm dividing the weight vectors. So I'm going to call this a promotion step, and this is a demotion step. Just like in Perceptron, when I'm talking about the Boolean variables, I actually don't touch those weights that correspond to xi's that are 0. Right? This is the case also in Perceptron, as we mentioned last time. Okay, so again, this learns linear threshold functions. Notice that if I know ahead of time, again, it's just a theoretical argument, but it's good to develop this understanding. If I know that I'm looking for disjunctions, I can replace this demotion step by an elimination step. That is, I can replace wi by 0. Why is that okay? Again, the scenario is the following scenario. I know that it's a negative example, but my current hypothesis thought it's a positive example. I exceeded the threshold. I'm claiming that a way to update the weight, the corresponding weight, is if xi is 1, if the feature is on, I can just replace wi by 0. Why is this okay to do? It's a disjunction. So what? So what?
So we have negative examples.
So it's a disjunction, and I know that it's a negative example, and I know that xy I is 1. So what do I know about this xi? It's not in the disjunction. Yes? Yes, it's a monotone disjunction. Okay, excellent. Thanks. I know that xi is not in the disjunction, right? Because otherwise, when it's on, it should have been a positive example. Yes?
The other ones could have been on too. Like xi could be on, but the other things which were in the final disjunction could be on.
Yeah, but I want to think about wi, the weight that corresponds to xi. All I'm claiming here that I can zero it out because I know that the ith component is unimportant. Right? So if I put wi equals 0, it basically indicates that I'm never going to look again at the ith feature, because the dot product is always going to zero out in the ith component. And I'm saying it's fine because I know that the ith component is not important to the disjunction. Why do I know this? Because it's a positive example. It's a negative example. I thought it's positive, and xi is 1. If xi is 1 in a negative example, it means that it's not important. Otherwise, it would have made the example positive. Okay? Yes?
In your usual linear separators that you've done, your weight vectors, your weights could be negative. But in this case, because weights do not get negative, that is why you're using elimination? Because otherwise, in a linear separator, if x was 1 and if x was 0 and you were dealing with
Okay. Very important point that we'll get to in a second. So basically what you're saying, you are not learning a general linear function because you start with weights that are 1 and you only multiply and divide by a positive number. I'm writing it here as if we are using 2. In fact, in practice, you'll probably use 1.1 or something. It doesn't matter. And therefore, the weights are always going to be positive, which means that the function that you're learning is only monotone. You're right. So as we said, it's just monotone function. For now, let's wait a few more slides and we'll generalize it. For now, I'm learning monotone linear functions. Yes?
Instead of make wi 0, here we just divide it by 2. We can increase the factor for xi. So future, if xi happens again, we divide it again by 2. So
We either divide it by 2 or multiply it by 2, depending on whether the example is positive or negative.
right.
Yeah. So let's go over an example here, and we'll see what happens. So just to develop some intuition. So my target function is this. I have 1,000, well, a computer science 1,000 features, and only 4 of them are actually important, but you didn't know that. Your algorithm did not know that. So I'm initializing theta to be 1024 because I know that this is n, and the weight vector is all 1. I see a first example, it's all 1s, it's a positive example. Well, my dot product also thinks it's a positive example because the dot product is going to be exactly 1024. Nothing happens. Second example, it's all 0s, it's a negative example, as you can see. My dot product also thinks it's below threshold. Nothing happens. I still have, as my hypothesis, the all 1 vector. Okay? Example number 3, 0, 0, a lot of 1s, and also 0 in the 1024 case. What's going to be the dot product here? I don't know exactly, but something that is less than 1024, right? It's less than 1024, but anyhow, it's a negative example, so nothing happens again, right? I didn't learn anything from this. I'm still staying with this as my hypothesis. Example number 4, 1, 0, and all the rest are zeros. Now, this is a positive example, right? Because it's a disjunction and x1 is on. It's a positive example, but the dot product is actually only 1, right? So I made a mistake. This is the first mistake I'm making. What am I doing? I'm going to double W1, the weight vector that corresponds, the weight coordinate that corresponds to the first feature. So now I have as my hypothesis 2 and the rest 1s. Here's another example. 1 is here, 0, a few other 1s in the middle. It's a positive example because of the x1. But the dot product, as you can see, is still below 1024. So I made a mistake again. What I'm going to do is duplicate this guy again. So now I have W1 here is 4 already, and I have a few others that are doubled in the middle. I'm going to do this again. Another example with x1 being on, a few others, and also 1024 is active. Yet, again, it's a mistake because I did not reach the 1024 with my dot product. And I'm doubling again. So for W1, I already have 8. For some others, I have other numbers here. Notice that after a bug log n, or log n over 2, examples like this guy is going to be 512 already because I'm doubling it. Right? After 9 times, it's going to be 512. After the 10th time, it's going to be 1024. So here is another example. Now I see 1, some other zeros here. This guy is also 1. It's a positive example. And now I'm already exceeding my threshold because I have more than 1024 in the sum here. Now, here's another example. Now x1 is 0. x2 is also 0. These are also 0, which means it's a negative example because the 4 important variables, none of them is on. But I thought it's a positive example. If I'm running the elimination version, all these things in the middle are going to disappear and become zeros. If I run the real version, the standard version, all these things in the middle will not disappear. They will just cut in half. So instead of the 256 here, I'll get 128. What's going to happen to this 512? Come on, louder. What's going to happen to the 512 here in W1? Not change. When will this number change? x1 is 0 here. It can change only when it's 1, because we do not update weights that do not correspond to active features. But not only it's 1 and it's a negative example. Can this happen? Cannot happen. So I will never shrink the size of W1. It can only grow. How much can it grow? It cannot grow more than 1024. Let's assume all the others are 0 here. If it gets to 1024, why can't it grow anymore? We'll never make a mistake, right? I'm exceeding the threshold. So this is the idea here, right? So it's going to grow, but because I double it every time, logarithmic number of mistakes is going to do it, and it's never going to go down. Right? Okay, so now, so this gives you some intuition. Now we can analyze it. The final hypothesis in this case, or a final hypothesis, right? There could be a lot of final hypotheses here, because I don't know what's going to happen here in the middle. It depends on the distribution of the data I see. All I know is that for sure, again, depending on the distribution, I will have enough mass in this 4 coordinate to every time when one of them is active, exceed 1024. Now, it could be that the distribution is such that x1 is always active with 1024. And therefore, I will not get them to grow to 1024, because I never see one of them on and the other one off. The important thing, again, from our perspective, is the mistake, the number of mistakes we're making, and we're guaranteed that it will not be too many. Okay, so this is very easy to understand because it's a disjunction. The same algorithm, by the way, is going to work also for conjunctions. In fact, for any monotone linear function, only that it's a little bit harder to see, because if you think about what W should be for a conjunction, it's a little bit more complicated. But what we're going to prove is that it's okay for disjunctions. Yes?
So it seems like the theta, initialized theta is very important. In this algorithm, theta never change.
Yeah. So the fact, you're right. In this algorithm, I did not change theta. And the fact that I initialized theta to be n is important in this algorithm. Yeah.
So is this theta the optimal one? Maybe the optimal one should be...
So I don't know 4, and I know n. It's a very good question. So what should the right theta be? So what do I know when I start learning here? I know the dimensionality. I know n. I don't know how many of these n variables are actually important in my target function. Had I known, maybe I could set up theta differently. But this is one of the parameters that I'm trying to learn. And as we said last time, in fact, it's NP hard to learn exactly the minimal number of elements in the disjunction or the conjunctions. So this algorithm is not going to learn this number. In fact, as you could see, I learned something like this here. Right? There could be some numbers that are non-zeros in the middle. I will not know whether these variables are important or not. All I know is that I stopped making mistakes. Right? So I can initialize it to n because I know n. I cannot initialize it to anything else.
Also because this is also a Boolean variable for every x.
It helps me here that it's Boolean variable, but we're going to write this algorithm in general way. I'm playing now with Boolean variables because it's very easy to get intuition and to prove a very interesting theorem, which is this. So I'm going to argue that Winnow makes k log n mistakes on k disjunctions. So again, the game here is we are playing with monotone disjunctions. We know that only k out of the n variables are on in the target function. We don't know which k are. And I'm going to show that the number of mistakes grows logarithmically in n and linearly with n. So this is the algorithm again. And in order to count how many mistakes, I'm going to split the count to two parts. The first one, I'm going to count how many mistakes it makes on positive examples, how many promotions will the algorithm make, and then how many mistakes it's going to make on negative examples. The sum of this is going to be the number of mistakes the algorithm makes. So let's just do it. So the first thing, I'm going to prove that u, the number of mistakes on positive example, is bounded by k log to n. So let's think about why is this true. What happens when I make a mistake on a positive example? Let's think about one of the important variables, the one that is in the disjunction. What's going to happen to the weight of this? It's going to double. How many times can it double? The worst case is going to be that this variable is the only one that is active in the example. All the rest are zeros. I don't touch all the other weights. And every example has this important variable on. The rest are zero. And of course, it's a negative example. How many times can it be a negative example? Log n or log 2n, depending on whether I do equal, less than or less than equal. Right? Because once I did it log n times, I doubled it log n times, so I got to the threshold. I will never make a mistake on it. So it goes up. What about going down? So this weight can go up log n times and stop. Can it go down? Someone said something. Can it go down? Why can't it go down? Because it's a disjunction. This variable, if it's on, it's a positive example. I will never demote it. So really, this is the argument. A weight that corresponds to a good variable is only promoted. Right? That's because it's a disjunction. And when these weights get to n, there will be no more mistakes on positive examples. Now, the worst case is that the example sequence is going to be such that I'll have to promote each important, each good variable separately. Right? So log 2n or log n, it doesn't matter, for each one. And there are k important variables, so it's going to be k log n. Okay? So very simple proof for this. Now I want to reason about V, the number of mistakes on negative example. It's going to be a little bit more complicated. Again, I'm going to argue that the number of mistakes on negative example is no more than twice the number of mistakes on positive examples. In order to reason about it, we're going to talk about the total weight. Right? So the total weight of all the weight vector that we have. At the beginning, we start with a total weight, which is n, right? Because I initialize everything to be 1. What happens when I make a mistake on a positive example to the total weight? It's a positive example. I'm promoting. So what happens to the total weight? It goes up by how much? So one way to think about it, it can go up twice. I want to say it goes up by no more than n. Why? It's a positive example. But I made a mistake. What does it mean that I made a mistake? It again? I think it's negative, which means the dot product is less than n. So when I double it, I'm not gaining more than n. Okay? So basically what I'm saying here, that a mistake on positive, I'm going to if I add n to the total weight I had, it's greater than what I'm going to be, where I'm going to be. Okay? Because I thought it's negative. So I cannot add more than n. Similarly, when I make a mistake on negative, it's going to go down, right? Because I'm demoting the weights. By how much would it go down? Why it's most n over 2?
So not every.
So it's true that not all xi's can be 1, but it's important here that I made a mistake, right? So it's a negative example. I thought that it's positive, which means what was the total weight? Greater than n. Now I divide it by 2, so I subtract more than n over 2, at least n over 2. Right? Because it was more than n. When I divide it, I subtract at least n over 2. So if I subtract n over 2 from where I was, I'm still greater than where I'll be after the update. Okay? Because I subtracted more than n over 2, for sure. Otherwise, it wouldn't have been a mistake. So with these two together, here is what I get. I have this total weight. It's always positive. I started with n. U times, I added at least n. V times, I subtracted at least n over 2. So this is the range I have for total weight. Now, if you look at this and you say, OK, so it must be positive, and you move things to the other side, you'll get that V must be no more than 2 times U plus 1. OK? So really very simple argument, and I think beautiful argument, that shows that altogether, I add U plus V, and I get that the number of mistakes is going to be K log n. Now, this is a general statement, as you'll see later today, but I'm not going to prove it in the general case because it's complicated. But hopefully, this gives you an idea that I moved from very nice additive update of Perceptron to a multiplicative update with Winnow, and I got some properties that I couldn't have imagined with the additive algorithm, right? Now, I'm actually adapting much quicker to the fact that my hypothesis space is very sparse. I only care about K out of the n variables. OK. Questions about this? So let's just summarize where we are. So in both cases, we are playing with examples that are either Boolean or real-valued, even though we argued about, Winnow only in the Boolean case, but you can run the algorithm otherwise. It's a mistake-driven algorithm. We have one family of algorithm that is additive. W is going to be replaced by W plus YX. Right? I'm adding the feature vector or subtracting the feature vector, depending on whether y is 1 or minus 1. And as we'll see, there's a lot of variation for this example of this algorithm. We'll see it in a few minutes, but this is the core algorithm. For Winnow, it's a multiplicative update. Recent algorithm, relatively recent, late 80s. And in fact, there's still a lot of work, or there has been a lot of work on it in the last 10 years. And actually, it's multiplicative update. I can think about it this way. So I'm replacing W by W times something. I'm writing it here as E to the label. So replace E by 2 or by 1.1. So it's either I'm multiplying it by 2 or dividing it by 2, depending on whether y is 1 or minus 1. Very simple algorithm. And I also write here the case of the Boolean features, because these are important cases. In many, many cases, we deal with Boolean features, and that adds a lot of efficiency to both algorithms, because you actually touch only a small subset of the weights, those that correspond to the active xi's. Okay, so there are many extensions to this algorithm. And in fact, you cannot run the basic algorithm as is. You have to extend it with a few of the extensions I'm going to discuss, because this is where it's going to shine. Some are, as I said, necessary for them to improve well. There is a notion of regularization. I'm going to say what it is and give examples, even though we're going to prove that we actually need regularization and motivate it a little bit later in the next couple of weeks when we talk about learning theory. Some are just for ease of use and for tuning. For example, often we want to convert the output of the classifier. The output of the classifier is a dot product, WX. It's a real valued number. And I often want to convert it so that it will be between 0 and 1 and will behave like a probability distribution. So I can say that the probability of y being 1 given x is the probability of something. So there is a simple way to convert it. Basically, I showed it last time. It's 1 over 1 plus e to the minus w dot product x times some constant a. The constant a could be 1, or you can tune the constant a so that it looks better, behaves more like a probability distribution. And there are a few other extensions that we're going to get to a little bit later. So I want to start with how do we regularize perceptron. And the key concept here is something that is called average perceptron, which really takes a perceptron, kind of an algorithm from the 50s, 60s, to be a very, very good algorithm, competitive with all the other linear learning algorithms that were developed, some in the last 10, 20 years only. So average perceptron is motivated by the following consideration. So we analyzed it as a mistake-driven algorithm, right? We analyzed the mistake bound, and we showed that there exists a mistake bound. But really what we care about some global guarantees on the performance. I want to be able to say, I ran my algorithm. Here is a new example. What's the probability I'm going to make a mistake on it? Right? That's really what I want to do. And it turns out that you can do this in a general way. You can convert every mistake-bound algorithm or every online learning algorithm to something that has these type of generalization capabilities. And in order to understand this, the key thing is to think about it in the following way. So you run your perceptron. You got an example, you did not make a mistake, you're happy, you keep your hypothesis. Here is another example. No mistake, you're happy, you keep the hypothesis. Here's another example. Now you made a mistake, you update your hypothesis. And that was the last example. You freeze it, and you give someone the model that you've learned, the hypothesis. Now, which hypothesis is better? The one you just ended up with, or the one you had just before you made the last mistake? Not a question that has a yes or no answer, but it's a question you have to think about. So what can you think about when I ask this question? So maybe the last example was noisy or something I don't care about, and before I had a pretty good hypothesis, and I want to regret the fact that I actually changed the hypothesis now. How would you know that before you had a pretty good hypothesis? A way for you to, just kind of an intuitive way to say, you know, the one before this last change was pretty good. Yes?
Maybe it's the number of samples before.
Fine, that's a very good idea. So let's assume you ran through this 1,000 times, 1,000 examples, you made no mistakes. It's a pretty good hypothesis. And now you hit on one example, you changed it. Maybe you didn't change it a lot. It depends on how many weights actually got changed. But you changed your hypothesis, and now you're done, and you're sending this last hypothesis to someone. Maybe it's not as good as the one you had before that was robust over 1,000 examples. Yes?
It depends if you made this mistake, then you change your hypothesis. Then you use this hypothesis to test the all right.
Okay, so it's possible for me, once I change the hypothesis, as you suggest, to go back and run again on previous examples. But before we get to testing, I just want to think about the fact that when you run a mistake-driven algorithm, it's not necessarily the case that the final hypothesis you end with is the best one, right? I want to smooth it a little bit over what has happened in the past. And this is what average perceptron are going to do, and it's going to implement exactly this intuition. If you run over a large sequence of examples with making no mistakes, it's a pretty good hypothesis. If you make rapid mistakes and you change your hypothesis every time, these hypotheses are not as robust. What we're going to do is we're going to implement this and convert a mistake-bound algorithm into a pack. We don't know what pack is yet, but something that has good generalization properties in the following way. We're going to wait for a long stretch without mistakes. In fact, when we try to quantify it, we'll see that there must be one that is like that. The hypothesis at the end of this stretch, the long stretch, can be shown to be good because we learned it over, it was robust, it is consistent with a lot of examples, right? It made no mistakes on a lot of examples. Now, in average perceptron, we are taking this intuition in the following way. We return a weighted average of a number of earlier hypotheses where the weights are a function of the length of the no-mistake stretch. Okay? So we actually keep everything as we learn. Every hypothesis that we keep it with the length of the stretch it was supported by. Sort of the number of examples we went through without making mistakes, and that's going to be the weight. So in practice, this is what we're doing. So this is a little bit more formally. So we're going to train in the following way. Again, the notation is M is going to be the index of the examples. K is going to be the number of mistakes I'm making, which is the same as the number of hypotheses, right? Every mistake, I have a new hypothesis. And I'm going to, the count, the consistency count, is going to be C. CI for hypothesis VI, which is going to count the number of times I lived with this hypothesis without changing it. So this is my sequence of input. And the output is going to be a list of weighted perceptrons, each one with the corresponding weight. I'm initializing everything to 0. And then for I equal 1 to M, I'm predicting. Now, the predicting is with my current hypothesis, VK. So it's the sign of dot product VK with the ith example. If I did not make a mistake, right, if the prediction is right, I'm increasing CK. I like this VK, the hypothesis, the kth hypothesis, and I'm increasing my count, my consistency count for it. If I did make a mistake, I'm updating VK. Now I have VK plus 1. This is the perceptron rule. And I'm initializing the count. I'm starting again from 1 for this K plus 1, right? Very natural algorithm. At the end, when I'm getting this final list of pairs, weight vector, number, weight vector, count, I'm predicting this way. So I'm doing the sine of vi times x on an example x, multiplying it by ci, and the sine of this. So basically, I have an average of my decisions. And this turns out to be a very good algorithm. So this is one key extension of Perceptron. Here is another key extension. Perceptron with margin. So essentially, we discussed this a little bit earlier. Perceptron really learned a linear separator. What I want to make sure is I want to try to learn some kind of a thicker separator. The way to do it is to be a little bit more aggressive in penalizing Perceptron. For example, I'm going to promote not only if wx minus theta is negative, and demote if wx minus theta is positive, but rather if it's less than some number, and demote if it's greater than some positive number. This number can be tuned. So essentially what I'm saying is I'm actually imagining a thick separator here, and I really want my positive example to be outside this line, the dotted line here, and my negative example to be outside this dotted line here. If they are inside, I'm going to treat them as mistakes and push them in the right direction. So I'm a little bit more strict. Now, one caveat, of course, is that this gamma is a functional margin, right? So it's not a real margin, as we'll define in a couple of weeks, in the sense that it's a fixed number. And as you learn and W grows, you could say, well, the effect of this gamma is going to disappear. Nevertheless, it turns out that it's a very effective algorithmic addition to Perceptron. Okay, the last extension that I want to talk about is the following. So several of you have asked the question, and I'm going to ask you now again. Let's assume I updated my current hypothesis with respect to this example. And then you give me the example again. Will I predict it correctly? Yes, no? Two options. What do you think? Depends on R. In general, no. It could be that I made a mistake on an example. I updated my hypothesis with the Perceptron rule. You give me the same example again, I'm still making a mistake on it, right? Because I did not update enough. Now, this may not be a problem, because you can feed this example multiple times. Eventually, I'll get it right. But you can also say, you know what, I want to make sure that when you give me the example again, I do not make a mistake on it. In order to do this, you have to update your learning rate, R. And it's a little bit of algebra to see that what you want to do is you want R to be this. Just, you can do it yourself, simple exercise. And if you do it this way, you guarantee that the same example, if you give it again, you will not make a mistake. So it's really equivalent to updating on the same example multiple times. Okay, so there's a lot of other extensions. Most of them are implemented in Snow or in LB-Java, which is the tool that you've seen, both for Perceptron and for Winnow, and a couple other algorithms. So I'm not going to talk about all this. Later today, I'm going to start to talk about extensions to Winnow and talk about a few other more sophisticated, in some sense, extensions. Okay, so we're going to meet today at 5 here. Hopefully, most of you can make it. See you. Hi. Sorry. No. I do have an idea.